Okay, so this is the final normal lecture for ELE 385. And today we're going to discuss branch prediction, which is, I've alluded to this in other lectures, where if you're doing branching and you're trying to do parallelism and you're trying to implement multiple instructions at the same time, what you're going to be needing to do is you're going to have an if statement executed here, but then you're going to have other actual aspects of the statement being executed. So you actually need to figure out whether or not you're actually going to do these or not. And so branch prediction, we're going to formally define it as a digital circuit that attempts to guess the result of a branch before the instruction is executed and the required information for the branch is known. So without branch prediction, we have to wait until the conditional jump instruction has passed the execute stage before the next instruction can finish the stage in the pipeline. Now recall in the data path that once you do the execution stage in the arithmetic logic unit, that's what's going to give the 0 bit, it's going to be ANDed with the branch control signal. You'd have to wait until that. So now with branch prediction, you're going to try to avoid this waste of time by trying to guess whether the conditional jump is most likely to be taken or not taken. So as we go over the problems, you're going to see that this is a term that we're going to use quite a bit, taken or not taken. The branch that is guessed is most likely then fetched and speculatively executed. So what I mean by speculatively executed is we continue to execute until we actually get to the execution stage in the pipeline, and then we find out whether or not we are actually going to do that. So here's a simple example. So we have I is equal to L, J plus plus, and then K plus J. So we have branch not equal. So we have S1 and S5. So I is S1 and L is S5. We branch one instructions. We have PC plus 4 goes to J plus plus. So we would actually go here. And then add I, J plus plus, and then add K plus equals J. So let us assume that the value of I is input by the user in real-time execution. And there's no way we can know whether to continue the execution or not until we actually do this. It's not something that can be driven by the compiler. So if branch prediction guesses incorrectly, then the values of J and K will be incorrect. So we're going to do with two different things. We're going to deal with static and dynamic branch prediction to deal with this problem. Static branch prediction uses information that was gathered before the execution of the program. So what this here means is that you're going to be running a number of different loops and while loops and for loops, and based on that, you're going to be trying to guess a probability that you're going to be running this. And then dynamic branch prediction, we're going to be learning about a specific type of dynamic branch prediction called 2-bit branch prediction. Uses information about taken or not taken branches gathered at runtime to predict the outcome of the branch. And so this actual 2-bit branch prediction, we formally define this as maintaining a branch prediction buffer or a branch history table recording the last behavior of the branch. So it's going to be 2 bits, and so we're going to have taken, not taken. So it's going to be a 4-value diagram where we're going to have small memory buffer indexed by at least 2 of the least significant bit of the branch instruction address. And so I'm going to scroll down here and show you what that means. So we have, so let's compare a branch prediction finite state machine versus the actual definition. So we have taken star, which is where we're going to start. You have T star N star T, and N star N. So if we have a start with the initial state of taken, so in order to actually predict that the branch is going to be not taken, we have to get 2 consecutive branches with their not taken, right? So if I have taken, I'm at taken star and it's not taken, then I go here to taken star N, but I'm still going to predict taken. So I'm going to predict taken, and if it's taken, we just go back here. Right? If we start at N star, what's going to happen is that the branch has to be taken twice before we get up here. So if you're in a loop that's in 100 times, what's going to end up happening is that no matter where you start, so it's going to take in, and then if it's I equals j, and then we get the first two if we're not taking it, and then we're not taking it, and then we do the loop 98 times, well, we're going to guess correctly more times here. And that's the benefit of branch prediction. And so we end 29 with this finite state machine diagram. 6.29 will be an exam question. Example 6.2. So we're going to actually go over this, and this is all you're going to be given on an exam. So the exam question would be the combination of TGO 6.29 and example 6.2. So I would say define 2-bit branch prediction and draw a diagram. So this would be the first part. And then the second part would be, given the 2-bit branch prediction method with initial state of n star and the following set of branches, describe the set of branches. So you are going to be basically given this. And see, the actual corresponds to these values. And so what's actually going to happen here? So if we start at n star, then I'm going to do dark blue so it becomes even. So starting at n star means that we're here. So we're going to predict n. So if it's not taken, then we stay at n star. So the first thing you would do is just draw these out for actual. So this one would be n, n, t, t, n, n, t, n, and n. So if you're starting at n star, you're at state n star, and predicted, you're going to predict no. Well, it turns out you're not actually taking it, so you're going to be at n star again, and you're going to predict no. Well, it turns out here that you're supposed to take the branch. So now we move to, we're actually going to start here. We're going to predict no, but now we're wrong, right? So this is the initial state. That's the state we're going to start. This is the initial state. This is the state we're going to start here. So here, instead of being n, it's going to be n star t. Does that make sense? And from there, we predict n, and we're correct. So it goes back. So we've predicted wrong. So it's here. And so now we're at t star. That's what I'm trying to draw up here. So if we're at n and we're at t star, what's going to happen is we're going to predict taken. Well, we're wrong, so now we're going to go to t star n, and we're going to predict taken. And then turns out we're wrong, so we're going to go to n star. So we're going to predict no, and we're wrong. So we're going to go to n star t. So now we're at this column. We predict n. We are correct, so now we'll go to n star. And that's this column. So the last thing we're going to be going over in this course is the concept of multi-threading. And this is something that's going to be discussed quite a bit when we get into Tensilica processor fundamentals. And so I would expect 6.30 to be on the exam as well. What is multi-threading? So what seems redundant to define multi-threading is performing multiple threads of execution in parallel. So what it allows us to do is if you have multiple data paths and you're able to replicate registers, program counters, and have fast switching between the threads. Now, there are 3 types of multi-threading that we're going to cover here. We're going to cover fine-grained, coarse-grained, and simultaneous multi-threading. So fine-grained multi-threading, we define here switching the threads after each cycle, and we're going to interleave instruction execution, and if one thread stalls, we're going to start executing the other threads. And I have a diagram down here after the topical guide objective that shows precisely what this is. Coarse-grained multi-threading only switches on long stalls. So now we're talking about kind of a level 2 cache miss. However, it's going to simplify the hardware, but it doesn't hide your short stalls. So there's your trade-off. Good design requires good compromise. And last and certainly not least, we're going to talk about simultaneous multi-threading. So we're going to have a multiple issue dynamically scheduled processor. So what this means is we're going to schedule instructions for multiple threads. You have instructions available from independent threads execute when function units are available. So what's going to end up happening is that's going to be interleaving between these threads. And it's going to require a good amount of overhead. However, within threads, dependencies handled by scheduling and register renaming. So this concept of register renaming, we're going to briefly touch on it here. You can go into this in quite a bit of detail into an advanced computer architecture course. The whole idea is that you're going to be renaming registers in the loop in order to, meaning that you're going to allocate multiple registers to a specific variable, and this will allow you to kind of churn through the loop faster instead of worrying about data. The whole idea is you're eliminating data hazards. And so here's what this means. All right, so here we have 4 threads. And so these are just 4 threads of execution and how we're actually going to go about using them. So thread A needs 2. In the first cycle, it's using 2. Second cycle, it's using 1. Third cycle, it's using 3. Fourth cycle, it's using 2. Fifth cycle, it's using 4. And now 1 and 3. Likewise with thread B, thread C, and thread D. So let us compare what coarse grain, fine grain, and simultaneous multi-threading are. So coarse grain is every cycle, we're going to keep going until we encounter one of these stalls, one of these big stalls here. So you see how coarse grain is using everything from thread 1? And then we hit a stall, and then what's going to happen is you're going to see it go to thread B. Now it keeps going like that. Now fine grain multi-threading is using the first cycle, it's using the cycle from A. From the second cycle, it's using the first cycle of B. Third cycle, it's using the thread of C. Fourth cycle, it's using D. Fifth cycle, it's using the second cycle from A, and so forth. That's fine grain multi-threading. Now, simultaneous multi-threading knows that we have 4 processors, so we're trying to allocate as much as possible. So the first set goes here, and then the first 2 processing elements from thread B go here. The second cycle, we use this one, and then all 3 from thread C. In the third stage, we're using this correlates here, and then we can fit this there. And so now there's nothing and there's nothing, so then what's going to end up happening is the next 3 are here. And then thread D, these 3 here are there. So it's just basically filling them all together. So it requires a good amount of overhead, but you're improving your throughput. So what we would normally be having is you would have to execute A, execute B, execute C, and execute D. In coarse grain multi-threading, I'm executing A until I encounter a stall, and then I'm executing thread B, and then I'd be executing thread C when I get here. After 1, I'd be executing thread D, and then I'd be going A. After that's done, I do B, then I do C, and then I do D. So it's significant. So it is improving it, but not as much as fine grain, because fine grain, every single cycle we're using something up. So what ends up happening is that when you encounter a stall, you're actually just going to move on straight to the next thread. And simultaneous multi-threading is trying to use every bit as much as possible. And so I believe this is this is it. It's the last topical guide objective for the lecture. So what we're going to do is there's this concept here called single issue multiple data versus multiple issue multiple data. And we're going to be talking about how you execute the program, how everything is operated, how you decode instructions, loop handling, which is kind of what we touched on with branch prediction. And then interprocessor communication. How do you actually communicate between multiple processors? So the program in single issue multiple data, we only have one copy of the program. Versus multiple issued multiple data, every program has its own, every processor has its own copy of the program in instruction memory. Now in operation, the processes operate synchronously on one program, whereas with multiple issue multiple data, the whole goal is to have multiple processors working on acting asynchronously on multiple programs. But we can actually use MIMD in the same way as SIMD. So it's not limited in that way. So instruction decoding, one instruction decoder in the control unit. So instead of having each processor having a program counter that points to instruction memory, and then we decode using the control units, and then the RS, RT, RD as we learned in the MIPS data path. That's done in one data path, and then it spreads to all the different processors to do all the different instructions. Whereas with multiple issue multiple data, each processor has its own decoder. So with loop handling, one control unit handles incrementing and decrementing throughout the loop, while each processor does computations and the execution of branch judgments. Branch jumps are serialized. So in multiple issue multiple data, that's different. We kind of talked about what we're doing with branch prediction, where each processor increments, compares, and computes. For conditionals, each processor acts as if it is a uniprocessor. And then finally, how do we actually communicate between all of these different processors in multiprocessing? So interprocessor communication is communicating operations are automatically synchronized. However, with multiple issue multiple data, you actually have to explicitly synchronize and identify protocols. And the reason why is because in MIMD, it's designed typically to act asynchronously on multiple programs. However, since processors can be used like single issue multiple data, we do need to explicitly synchronize and identify protocols in that case. So we're going to finish here, and we are going to start Cadence on Thursday. And I'm going to open up lecture at the beginning to anybody who has any questions. We're going to go over the type of stuff that we're going to expect on the exam. So I want to kind of go through section 6 really quick and tell you what I'm expecting. I expect you to be able to answer a question like 6.1. I expect you to be able to tell me what virtual memory is and the two motivations. .15, the one that I provided for you. I expect that one's going to be on the exam. And then I expect you to be able to define and differentiate between instruction level parallelism and thread level parallelism. You are going to be expected to write through versus write back. It's a definition, 6.24. And cache coherence. Define cache coherence and define and differentiate between write through and write back. You should know directory-based coherence and Snoopy bus protocols. You should be able to tell me, you should be able to define 2-bit branch prediction. You should be able to draw the finite state machine. And you should be able to, given a set of branch predictions, solve for this. And then last but certainly not least, I expect you to be able to tell me, define multi-threading and tell me to differentiate between fine-grained, coarse-grained, and simultaneous multi-threading.